Okay, so in part one, the introduction to this worksheet, and let's take a look here. We're dealing with chemical quantities, practice problems, and the focus is percent composition and empirical molecular formulas. In the last video, we did number 2, and now we're ready for number 3. And let's just remind ourselves what we're trying to do. It says determine the empirical formulas for compounds that have the following results from elemental analysis. Okay, so these are, these are data. We were imagining that we sent a sample to a lab, and we asked them, hey, what's in this sample? And give us an elemental analysis. And what we get in return is a report telling us first what elements are present in the substance that we submitted, and furthermore, what is the percentage in terms of mass of that sample by, from one element to the next. So here we have a sample which had 2 elements, rhenium and oxygen, and these are their percent compositions by mass. Okay, so let me go over to the PowerPoint here where I've got a little more space. Remember the trick? We first, in order to figure out the empirical formula, we need to figure out what the masses are, and then get that into moles. So we're going to assume that we have 76.89 grams of rhenium. Okay, so that's the rhenium content, and the oxygen content is 23.12 grams. All right, so this is a nice little trick that we use to convert the percent composition into grams, and then from grams we know how to get moles. And this works because by assuming that we have 100 grams of sample and turning these percentages into grams, we are maintaining the exact proportion of, among the elements. We're not changing that composition at all. So this is a nice little trick that we use. All right, so how many moles? So the number of moles equals 76.89 grams divided by the atomic mass of rhenium, which is 186.2 grams, and that gives us 0.413 moles. All right, what about oxygen? Okay, so to get the moles of oxygen, we take 23.12 grams, divide by the atomic mass, 16.0 grams, and we find that we have 1.445 moles of oxygen. All right, so now again, let's read the problem. Problem is saying find the empirical formula for these compounds. Okay, so how do we approach that? Well, the empirical formula is going to look something like this, where we have the amounts, the mole ratios for subscripts. So what we can write at this point is 0.413. That's what we got for rhenium, and for oxygen we have 1.445. Okay, and that is the mole ratio. That's what an empirical formula is showing you. However, in order to be a true empirical formula, we have to have the lowest whole number ratio between these two. So in order to get there, what we do is we divide both mole values by the smallest mole amount. And when we do that, that then converts to rhenium 1. And let's see, what do we get when we divide 1.445 by 0.413? 445 divided by 0.413, and I get 3.498 789 and so on. Okay, I'm not going to bother. There's more digits, but you know, it gets ridiculous. They're not significant. All right, this ratio, or I'm sorry, yeah, that ratio between the oxygen and the rhenium moles is quite close to 3.5. All right, and so what could we do? Let me rewrite this here. What could we do now to convert this ratio into a whole number ratio? Well, turns out that if we multiply both by 2, we get rhenium 2, oxygen 7. And, my friends, that is the correct empirical formula for this compound given the percent composition that we got from elemental analysis. And that's, you know, that's the procedure. So whenever you get a ratio, a number and then a decimal that's pretty close to 0.5, then you can be pretty confident that within experimental error, what that means is you've got to multiply by 2, like we did here, to get the actual empirical formula. Okay? Okay, let me just put this up here so I can keep track of my time. All right, number 4. Moving ahead. Number 4 is very similar to the last problem, and what I'm going to do here is just present the result. So what you should get is iron 2, chromium 3, oxygen 12. Okay, so that is the empirical formula for number 4. Number 5, same type of problem, and here the empirical formula that you should get is C6H5 F2N. Okay, and that's the empirical formula there. Now, obviously, tomorrow we can, you know, if you're not sure how we got those answers, we will certainly go over that tomorrow, but I want you guys to give it a serious try. Okay, now, the next problem, number 6, is a little bit different. This is now getting into molecular formulas. So it says determine the molecular formulas for compounds having the following empirical formulas and molar masses. Okay, so now there's 2 pieces of information. You're being given the empirical formula, which is this, and then the molar mass. Okay, and the molar mass corresponds to the actual molecule. All right, whereas remember, the empirical formula is simply the lowest whole number ratio of the mole ratio among the elements. All right, so how do we attack this? Well, step 1 is let's figure out what we would call the empirical molar mass. So the empirical molar mass. All right, what is that? Well, the empirical molar mass is you simply take the empirical formula and just calculate the molar mass for that. So here we've got 2 carbons, right? So that's 24.0. We have 4 hydrogens, so that's 4.0. And then we have 1 sulfur, which is 32.1. 32.1. And when we add all those together, you should get 60.1. That's 60.1 grams. All right, that's the empirical molar mass. Now, take a look at the molar mass, and let's see if we can figure out by what factor would we need to multiply this such that the empirical molar mass is equal to the actual molecular mass. Sorry about that. Okay, so that factor, or that ratio, would be 179. Whoops, 179.0. Sorry, I'm losing control of my pen here for some reason. 179.0 divided by 60.1. And when we do the math, let's see, 179 divided by 60.1, and I get 2.97 178. Okay, which is pretty darn close to 3. All right, so what we need to do is multiply the empirical formula by the factor 3, and when we do so, we get C6H12S3. There you go, and that is the molecular formula given these data, empirical formula and molar mass. All right, number 7, same thing. And the answer, which I'll just give you, is C8H16O4. All right. And again, I really hope that you're like attempting to work this. I hope you push the pause button before I give you the answer. All right. So number 8. So push pause. See if you can do this one. All right. Okay. So the empirical. What'd you get for the empirical molar mass? Molar mass. All right. You should have gotten right around 42. And the multiple between this mass and the molar mass of the molecule is 6. So you have to multiply this empirical formula by 6, which means the molecular formula is C12H12O6. And by the way, in class, all these months, whenever I say, hey, what's the chemical formula of that compound? Like water is, H2O, and ammonia is NH3, methane, CH4, propane, C3H8, and so on. These are all molecular formulas. These are all molecular formulas. It just so happens that they are also empirical formulas, because as they're written in the molecular formula form, they are giving the lowest whole number ratio among the elements. So sometimes the molecular formula is the same as the empirical formula. They're not always different. Okay, let me scroll down. All right, number 9. What's number 9 about? Let me go down a little bit here. Okay, number 9. Now we need to determine the molecular formula again, but we're being given a little bit different data. We're going to have to work a little bit harder for it. Instead of just being given the empirical formula right off the bat, we have to start one step back. They're giving us the percent composition data. We first have to determine the empirical formula, then we use the molar mass to get the molecular formula. All right, but that's no big deal. We are all over that. So number 9, I'll show you. Again, do the percentage to 100 grams trick, and when you do that, you'll find that you've got 3.45 moles of carbon, and you have 3.4 moles of hydrogen, and you have 3.45 moles of oxygen. Okay, now I think you can step back and already see that the mole ratios among every pair of element is going to be 1 to 1. Okay, so you can, right off the bat, you know that the empirical formula is simply CHO. All right, and that gives us an empirical molar mass, if you will, of let's see, 12 plus 16 is 28, plus hydrogen is 29, so 29.0. What's the ratio here? I think you'll find that the ratio is 4, and so therefore the molecular formula is C4H4O4, and that is a molecular formula given these data. Okay, so we're going to stop there, and there will be a part 3, so I'll see you there.